One thing you have to keep in mind when you're dealing with the aquatic environment is that it's not intuitive. We as terrestrial vertebrates have an inherent understanding of living in a dry environment and breathing air. In contrast, we have troubles understanding and empathizing fish. In order to fill that gap in understanding, we have to learn as much as we can about the aquatic environment. The aquatic environment can vary considerably in its parameters, from temperature to salinity to pH and levels of dissolved gases. Now, the gills are constantly exposed to the aquatic environment, and so the water chemistry can have a significant effect on the body chemistry. In an open environment, fish have the freedom to move to more favorable conditions. For example, a fish is likely to avoid areas that are oxygen depleted. When a fish is dealing with an infection, it can move to warmer areas to increase its metabolism and boost its immune system. However, in a captive setting, like one would expect to find in aquaculture, a fish's options are limited, so proper environmental management is of great importance. You also have to be vigilant and recognize changes in behavior that could indicate changes in water parameters. Various processes in the fish are temperature dependent, including growth, food conversion, disease resistance, and egg development. Many of these processes are codependent on the level of oxygen and the pH. Optimal temperatures vary between species. Optimal temperatures also vary between processes. In terms of disease resistance, infectious etiologies also have a preferred temperature range at which they're more likely to cause disease. For example, Bicirrhachetsis salmonis tends to produce outbreaks at higher temperatures. The fish's immune system will function best at a given temperature, and so an ideal temperature is necessary to keep the host-pathogen relationship in balance. Temperature has an effect on a number of other parameters. It's important to remember that an increase in temperature is associated with a decrease in the solubility of gas, like oxygen. An increase in temperature will also increase the solubility of pollutants. Generally speaking, bodies of fresh water experience a greater change in temperature throughout the year. This is because they have a lower volume than the ocean, and as a result, they have less inertia as far as temperature. Small volumes of water generally cool down or heat up a lot faster. The ocean is fairly consistent in its temperature because of its large volume and continued circulation. Surface temperature can vary throughout the year, but below the thermocline, the water temperature remains constant. The depth of the thermocline can vary. Light can vary in the duration of exposure, its intensity, and the quality of light, meaning the spectrum of wavelengths. Light exposure can be controlled through the use of shade, water depth, algae levels, and the use of reflective or absorptive surroundings. A common problem in aquariums is the use of reflective surroundings, or brightly colored surroundings. This can reflect ultraviolet radiation, causing damage to the fish's eyes. Light can influence the fish in other ways. For example, it can influence development and sexual maturation. Excess ultraviolet exposure can also cause sunburns. Certain drugs and feed components can cause photosensitization, which makes the fish more prone to ultraviolet radiation. Light can also have an effect on the aquatic environment by promoting algal growth. pH is another parameter that is unique to the aquatic environment. pH can be calculated, or the desired pH can be achieved through the use of a basic formula and the dissociation constant of the chemical in question. The formula is as follows: pH equals pKa plus the log of the concentration of the anion plus the concentration of the proton divided by the concentration of the undissociated molecule. pH can have an effect on the ionization of other compounds in the aquatic environment, which is why it's important to have a general understanding of this concept. For example, the unionized form of ammonia is much more toxic than the ionized form, also known as ammonium. The concentration of the unionized form will increase when the pH is more alkaline. The reason for this is that when the concentration of hydroxide is increased, it reacts with ammonium and shifts the equilibrium to produce more ammonia. Buffers are molecules that bind protons from strong acids so that small changes in the concentration of small acids will not alter the pH significantly. Now, the carbon dioxide, carbonic acid, bicarbonate, and carbonate buffer is a really important natural buffer in the aquatic environment and also in your body. Certain cations like calcium and magnesium bind to carbonate and shift the equilibrium to increase the availability of carbonate and bicarbonate. This increases the buffering capacity of the system. For this reason, saltwater systems which have an abundance of calcium and magnesium tend to be more pH stable. As a result, they are more resistant to acid and alkaline wastes. In contrast, freshwater systems are more prone to pH fluctuations. pH can affect fish growth and plasma ion concentrations. Abnormal ion concentrations in the plasma can result in a loss of movement. Generally speaking, fish can tolerate gradual changes in the water parameters, including pH. However, sudden changes can have a significant impact on the health of the animal. Fish naturally exist in a broad range of pHs, from a pH of 5 to a pH of 9.5. There is one species of fish in Kenya called Alcholapia grami. This fish lives in Lake Magadi, which is characterized by high salinity and in some regions temperatures of 80 degrees Celsius with a pH of 10. When a fish experiences a rapid decline in pH, it will attempt to jump out of the water. This is because a low pH will irritate the skin and gills. The fish may also increase mucus production as a defense. Gases vary in their solubility. The solubility is also dependent on the partial pressure of the gas. The three gases that are most often considered in the aquatic environment are oxygen, nitrogen, and carbon dioxide. Other gases that you should be aware of are hydrogen sulfide and ammonia, which are highly toxic to fish. Gases will naturally dissolve in the water at the air-water interface under the influence of atmospheric pressure. However, gases can also be pumped into the water column under higher pressures. This will increase the partial pressure of the gas and therefore increase the solubility of the gas in the water. This is great when you want to oxygenate water that is oxygen depleted. However, supersaturation can become an issue, particularly with oxygen and nitrogen. This can result in gas bubble disease, wherein you have an excess of dissolved gas in the water and by extension an excess of dissolved gas in the bloodstream. A sudden rise in temperature or a sudden decrease in the depth of the fish will reduce the solubility of the gases. This will cause the gases to exit the blood and form gas bubbles within the circulatory system. This can produce a whole array of lesions. In the image below, you'll notice large numbers of small blisters within vessels throughout the caudal fin. These are focal gas bubble infarcts. A similar condition has been described in scuba divers that ascend too quickly. This condition is known as decompression sickness, or the bends. The solubility of oxygen in water will decrease with an increase in temperature and salinity. For this reason, freshwater fish generally live in a more oxygen-rich environment. The partial pressure of oxygen in water drives oxygen across the gills into the blood. Relative oxygen consumption also increases with temperature as a result of an increase in the metabolic rate. In other words, in a warm water environment, not only do the fish require more oxygen to meet their metabolic demands, there's decreased availability of oxygen. The relationship between temperature and the solubility of gas is best demonstrated with a warm glass of water. When you pour a warm glass of water right from the faucet, you'll notice that it's cloudy compared to a cold glass of water. That's because the gases are no longer soluble in water, and so they're fizzing to the surface. Carbon dioxide is easily expelled from the body via the gills, so an excess of carbon dioxide is rarely a problem in fish. As previously mentioned, when carbon dioxide dissolves in the water, it produces a natural buffer. However, the relationship becomes a bit more complicated when you take into account that there are aquatic plants in the environment. During the day, the aquatic plants use carbon dioxide for photosynthesis. During the night, the aquatic plants generate carbon dioxide via oxidative metabolism. The fluctuation of CO2 can actually change the pH in small bodies of water. Although excess CO2 is rarely an issue, it can have an effect on the fish. Namely, it can decrease respiration, decrease plasma chloride concentrations, stunt growth, and impair immune function. Elevated carbon dioxide levels and low pH are more of a problem in closed containment facilities. This is because the volume of water is generally low, the stocking density is high, and the availability of oxygen is high, which is associated with increased metabolism and therefore an increase in carbon dioxide production. Ammonia is highly toxic to fish, even at low levels. It can cause disturbances in osmoregulation, and it can also cause irritation of the lamellar epithelium, resulting in lamellar epithelial hyperplasia. This can further interfere with gas exchange. High pH, high temperature, and low salinity can shift the equilibrium between ammonia and ammonium, resulting in a higher concentration of the toxic form. Carbon dioxide will decrease the pH and react with the unionized form of ammonia to produce ammonium carbonate, which is less harmful. For this reason, it's important to have a carbonate buffer in your aquatic system. Higher levels of ammonia are associated with a variety of factors, including overcrowding, which results in excess production. High-protein diets also result in excess ammonia production. New tank syndrome describes the buildup of ammonia as a result of a lack of nitrifying bacteria to break down ammonia into nitrite and nitrate. Antibiotics and disinfectants can destroy the population of nitrifying bacteria, which will have the same effect as new tank syndrome. In a recirculation system, the water has to be treated with biological filters in order to prevent ammonia toxicity. In the natural environment, the buildup of ammonia is prevented by the nitrogen cycle. In an artificial setting, we have to recreate the nitrogen cycle with our biological filters. How it works is when ammonia is produced, it is broken down by nitrous ammonium species of bacteria, which convert ammonia into nitrite, also known as NO2. Nitrite is then broken down into nitrate, NO3, by Nitrospira species and Nitrobacter species. NO3 will then continue to build up in the environment until it's removed. This is why in recirculation systems you need to exchange the water periodically. As previously mentioned, nitrous ammonium species of bacteria break down ammonia into nitrite, or NO2. However, although ammonia is more toxic, nitrite is also toxic. Nitrite is a fairly reactive molecule when compared to nitrate. Nitrite can bind to hemoglobin to produce methemoglobin. This creates the condition known as brown blood disease. Methemoglobin no longer has the bright red color that is characteristic of hemoglobin. Instead, it has a muddy brown color, so affected fish will actually have brown-looking gills. In addition to the color change, it also alters the oxygen binding capacity of hemoglobin, causing respiratory distress. Nitrite toxicity is associated with excess ammonia production, which in turn results in increased nitrite production. It's also associated with decreased nitrate production. In other words, you have a bottleneck in the nitrogen cycle, resulting in a buildup of nitrite. This can occur when you have suboptimal temperatures that favor the growth of nitrous ammonium over Nitrospira and Nitrobacter. Nitrospira species and Nitrobacter species convert nitrite, NO2, to nitrate, NO3. Nitrate is still a toxic molecule, although it is far less harmful. As a result, nitrate toxicity is more insidious. Clinical signs associated with nitrate toxicity include anorexia, lethargy, and disequilibrium. Histologically, you can expect to see lymphoid depletion, resulting in immunosuppression. Affected fish can also experience hemolysis, anemia, and jaundice. Nitrate toxicity is associated with old tank syndrome. This can occur when there are infrequent water changes, resulting in a buildup of nitrate and protons, the latter of which is associated with a drop in pH. The image on the right is a graph illustrating the exchange between ammonia, which is highlighted in red, to nitrite, which is highlighted in green, to nitrate, which is highlighted in purple. As you can see, periodic water exchange is necessary to drop the level of nitrate in the system. Undissociated hydrogen sulfide is extremely toxic to fish, even at low levels. Common manifestations of hydrogen sulfide toxicity include decreased food consumption, decreased endurance, tissue irritation, which can result in death, larval deformities, and a failure to hatch. When there is a low pH, there is a higher proportion of the undissociated form of hydrogen sulfide, which is more toxic. Hydrogen sulfide is produced via the anaerobic metabolism of organic wastes. This can occur on the ocean floor beneath salmon farms where there is an excess of fecal material. Any disturbance on the ocean floor can bring the hydrogen sulfide back up to the salmon pen. This can result in a mass mortality event. Some species of fish are naturally resistant to hydrogen sulfide. These species typically live near hydrothermal vents on the bottom of the ocean. Examples include Thermarces, Bithites, and Thermobiotes. Water salinity is defined as the total number of grams of salts dissolved in a kilogram of water. Changes in salinity can interfere with gill and kidney function, which in turn will interfere with the body's ability to maintain osmolarity of the body fluids. Salinity of the freshwater environment is largely dependent on the type of rock and soil in the area. Lakes and rivers that flow over limestone are generally rich in calcium, magnesium, and carbonate. Where there is an abundance of sand and sandstone, there are generally low levels of dissolved minerals. Groundwater can have an excess of dissolved minerals. For example, in some areas groundwater is very rich in iron, which can be a problem if you're using groundwater to supply your system. A high pH can decrease the solubility of certain minerals or facilitate reactions with other compounds, rendering these minerals biologically unavailable. In some areas, acid rain and acid snowmelt is an issue. Where there is bedrock, acid rain can extract aluminum ions from the substrate. When aluminum ions are present in high concentrations, they can cause mortality events by accumulating in the gills, causing chemical injury. In these circumstances, soil is quite beneficial because it acts as a buffer to neutralize the acid in the acid rain. This in turn prevents the extraction of aluminum. There are a number of other heavy metals and pollutants which can be harmful to fish. Examples include copper, lead, iron, mercury, zinc, chromium, cadmium, and manganese. These can be found in industrial discharge and mining wastes. Pesticides and parasiticides, like organochlorines and organophosphates, can be used in agriculture, which can run off into the aquatic environment. Arsenates, sulfides, phosphorus, fluorides, and halogens are other pollutants that you can find in the water, in addition to polychlorinated biphenyls and polyaromatic hydrocarbons, the latter of which includes gasoline and diesel. The images below illustrate a mass mortality event that occurred when a Kentucky bourbon distillery caught fire and released 45,000 barrels of Kentucky bourbon into the river. Algae can also have a significant impact on the health of the fish. The most common cause of algae-associated mortality is oxygen depletion. When you get a massive proliferation of algae, they require a lot of oxygen to replicate. So they essentially suck up all the oxygen from the surrounding environment, leaving none for the fish. Certain species of algae can also produce neurotoxins, hemolysins, hemagglutinin, and cytotoxins. Most of these toxins only affect higher vertebrates, like domoic acid, which is responsible for amnesic shellfish poisoning. However, there are certain toxins that can affect fish, including certain species of dinoflagellate, like Pfiesteria piscicida. This organism has certain life stages that are toxic. These life stages can produce neurotoxins, which can incapacitate the fish. They also produce cytotoxins, which can cause necrosis of the skin. Cyanobacteria, also known as blue-green algae, can produce a number of toxins. Microcystis is a genus within the group that is responsible for net pen liver disease. The toxin responsible is microcystin. This is a potent hepatotoxin that causes hepatocellular dissociation and hydropic degeneration and necrosis. The image to the right is a histological section of a mammalian liver after it was exposed to microcystin. There are also certain species of phytoflagellates, like Heterosigma akashiwa, which can cause gill damage, resulting in hypoxia. Certain species of algae cause mechanical irritation, particularly in the gills, which are delicate tissues. Chaetoceros is one such example. On the left is an image of Chaetoceros under the microscope, and as you can see, it has a very sharp silicate shell. Now, Chaetoceros can cause a lot of gill damage because it can act like a little spear, shoving its way into the gill filaments. The image to the right is a histological section of Chaetoceros caught in the act. In addition to environmental risks, there are also animal risks to aquaculture. Wild conspecifics and other species can act as reservoirs of infectious disease. Farmed fish can also share the habitat with intermediate hosts of various parasites with complex life cycles. Not only is this an issue for the health of the fish, but it can also decrease the value of the product and serve as a human health risk. With open net pens, small species of fish can actually compete with the farmed fish for food by swimming through the netting. Predation can also be an issue. Although there are certain species of fish that can prey on farmed fish, most of the predators that interfere with aquaculture are marine mammals and birds. Effluents of untreated and undiluted sewage can create a surge in the availability of phosphates, nitrates, and ammonia in a process known as eutrophication. This can result in algal blooms, which can quickly deplete the oxygen in the surrounding environment or result in toxin production. Effluents can also be a cause of food contamination. The risk of contamination is greatest during the handling, storing, and processing of the fish products. Sources of sewage include agricultural runoff. Examples include manure and fertilizer. Other sources include leaking septic systems, overboard sewage, and failures in waste management. Fecal coliforms are a good indicator of fecal pollution in the environment, so potential sources of contamination are tested quite regularly. Fish can also serve as a sentinel for pathogens of public health concern, so there is growing interest in the testing of fish. Next, we'll discuss some of the basics of fish physiology, beginning with fish blood. Fish generally have low blood volume, wherein blood will only make up roughly 5% of the body weight. The cellular component of fish blood consists of nucleated red blood cells, thrombocytes, neutrophils, which are involved in inflammation and have some phagocytic capabilities, monocytes, which are also involved in inflammation and the cell most responsible for phagocytosis, eosinophils, which are very rare, lymphocytes, which are involved in inflammation and the acquired immune response, and eosinophilic granular cells, which are unique to fish and believed to be homologous to the mammalian mast cell. Fish serum is similar to that of mammals, however fish have lower levels of plasma protein. Freshwater fish live in a hypoosmotic environment, which means that the water is continuously flowing into the body via the gills, the mucous membranes, and other permeable surfaces. This means that the kidney has to produce a large volume of dilute urine to rid the body of water, but in so doing there is a loss of ions. In order to compensate for the loss of ions, there is increased reuptake of sodium and chloride in the renal tubules, and increased uptake of sodium and chloride in the gills and the gastrointestinal tract. Consequently, freshwater fish are more susceptible to glomerular injury. In the marine environment, the opposite is true. So these fish live in a hyperosmotic environment, which means that the fish are constantly losing water through the gills. As a result, they produce a small volume of roughly isoosmotic urine, with a net gain of ions. In order to compensate for this, the fish has to drink constantly. Excess monovalent ions are removed through the gills. In elasmobranchs, they're removed through the rectal glands. Chloride cells, which were already covered previously, are located along the base of the gill lamellae. In the marine environment, these cells are responsible for pumping ions out of the body. When the fish is living in a freshwater environment, these cells are responsible for pumping ions into the body. Ammonia and urea are expelled from the gills via passive diffusion. Ion homeostasis is regulated via the endocrine system. As previously mentioned, anadromous fish are those that live in the marine environment as adults and migrate upriver into the freshwater environment to spawn. So when these fish hatch, they grow up in a freshwater environment and have to move back into the marine environment. In salmon, the transition from the freshwater environment into the marine environment is known as the parr-smolt transformation. In order to survive this, they have to undergo drastic hormonal and physiological changes. Now, in regards to fish metabolism, fish are ectotherms, which means that they're responsive to environmental changes. They're also poikilotherms, which means that their body temperature fluctuates. This means that less energy is spent on maintenance when compared to homeotherms. Most of the energy that they acquire goes to growth. For this reason, proteins are a more important part of the diet as opposed to carbohydrates. Now, if you look at the food conversion rate of the fish, it varies between 1 and 1.5. Compare that to the cow, where the food conversion rate is 4.5 to 7.5. This means that it's much more energetically expensive and inefficient to raise a cow than it is to raise a fish. As previously mentioned, carbohydrates are not an important dietary component in fish. Fish have a low metabolic rate, so they don't need to maintain high levels of blood glucose. Now, in a controlled laboratory study where they administered insulin, they were able to lower blood glucose and move glucose into the tissues. However, administering glucose did not produce a strong insulin response. A possible explanation for this is that the neurons normally have large glycogen reserves, and so there was no need to release insulin. So it's best to think of fish as diabetic, wherein feeding carbohydrates will cause persistent hyperglycemia. During periods of starvation, fish will rely on gluconeogenesis from amino acids as a source of glucose. Glycogenolysis is not a major source of energy. Lipids are important in maintaining cell membranes. Because fish exist in low environmental temperatures, they need lipids with low melting points. For this reason, omega-3 fatty acids are essential. Increasing the lipid component of the diet will improve protein utilization for growth. However, excess lipid can cause mortality via fatty liver. Proteins are a major source of energy in the fish, which make up 45 to 75% of the energy used. Proteins are also important in growth and gonadal development. In regards to the relationship between temperature and metabolism, the rate, extent, and direction of the temperature change can affect the metabolic rate. A rapid increase in temperature, even within a comfortable range, can kill a fish. The reason for this is that it pushes the metabolism beyond that which the oxygen in the blood can sustain. A rapid decrease in temperature can actually reduce oxygen consumption, and this can calm the fish, making the fish easier to handle. The optimal temperature varies between species, but once achieved, you can maximize conversion efficiency, growth, and performance. However, you're limited by the solubility of gas at higher temperatures. When you think of metabolism in a fish, you need to consider the balance between the level of dissolved oxygen in the environment and the permissible level of activity. The incipient limiting level is the level of oxygen above which the fish can move independent of oxygen tension. The zone of tolerance is the range of dissolved oxygen at which a drop in oxygen tension will result in decreased swimming activity. However, in spite of the drop in activity, the fish can survive in the zone of tolerance indefinitely. The level of no excess activity is the level of dissolved oxygen at which the standard metabolic rate is equal to the active metabolic rate. Any additional movement will result in an oxygen debt. In the zone of resistance, the standard metabolic rate is elevated. The fish has turned to anaerobic metabolism to meet its metabolic demands, resulting in the production of lactic acid. Any additional movement at this point is not possible, and the existence of the fish in this state is unsustainable. Oxygen requirements are dependent on a number of factors, including the fish species. Generally, fish with a higher body weight have a lower metabolic rate and thus have lower oxygen demands per unit mass. When there is insufficient oxygen, fish can experience decreased growth and reproduction. There is also a decrease in physiological and immune function and abnormal larval development. During periods of hypoxia, the fish can be seen gasping at the surface or exhibiting increased ventilation. Prolonged hypoxia will result in acidosis, eventually progressing to the death of the animal. When the levels of dissolved oxygen are low and the fish are at a high stocking density, startling the fish can increase the active metabolic rate, resulting in rapid oxygen depletion and mass mortality. For this reason, medical interventions must be timed accordingly. You're not going to be delousing an entire population of salmon when there's a slack tide and the level of dissolved oxygen is really low. Another important concept is what is known as specific dynamic action. This is the energy required to process food. Diets that are higher in protein take more energy to process. So if you're dealing with low dissolved oxygen and high temperatures, and you feed the fish a high protein diet, you can actually cause a mass mortality event. The next section will go over some of the aquatic environments you're likely to encounter, highlighting some of the important differences between them and the issues you're likely to face. Rivers and streams have what are known as headwaters. This is the source of the river or stream. Examples include marshlands, springs, groundwater, lakes, and glacier or snowmelt. The source of the water can affect the water parameters. Rivers and streams generally absorb salts and minerals from the soil and pick up silt as they flow downstream. They experience temperature fluctuations throughout the day, which is dependent on a number of factors, including the availability of shade, the depth of the river, the volume of the water, the altitude, and the flow velocity. Industrial and agricultural activity upstream can affect the aquatic environment downstream. Likewise, aquaculture activity upstream can result in the spread of disease downstream. So these are things you have to keep in mind, even though the river might look nice where you are. Lakes tend to be stagnant bodies of water, and as a result, they are prone to thermal stratification, which can be a problem. Thermal stratification is when the body of water is subdivided into different layers at different depths with different temperatures. The surface layer is known as the epilimnion. This layer is oxygen-rich, given that it's in contact with the atmosphere and subject to wind, rain, and other turbulent forces. The epilimnion tends to be of a higher temperature, though is more prone to temperature change and will fluctuate throughout the day and throughout the year as the seasons change. When combined with an increase in the availability of nutrients through the process known as eutrophication, the epilimnion can experience an algal bloom, resulting in oxygen depletion and algal toxin production. The hypolimnion is the layer on the bottom. Generally, it is oxygen depleted and cooler than the epilimnion. The temperature of the hypolimnion will remain constant throughout the year. The thermocline, also known as the metalimnion, is the junction between the epilimnion and the hypolimnion. It is a thin but distinct layer characterized by a rapid change in temperature. The depth of the thermocline may vary throughout the year. During the autumn, when surface temperatures cool, the thermocline will dissipate, resulting in a rapid turnover wherein the hypolimnion rushes to the surface. The rapid upwelling of oxygen-depleted water can cause a mass mortality event by suffocating any fish within the surface layers. Heavy rains can also punch through the thermocline. This can produce a similar effect. The use of groundwater has its advantages and disadvantages. One of the advantages of groundwater is that it's free of disease. Although the temperature remains fairly constant, the water chemistry must be closely evaluated because, as previously mentioned, the water chemistry is highly dependent on the rocks and the soil in the area. Groundwater also tends to be low in oxygen and rich in nitrogen and carbon dioxide. The temperature of the ocean is fairly stable. However, sheltered areas and shallow areas tend to be warmer because there's less turnover. Water exchange is dependent on tides, currents, and winds. You also have to consider the effects of freshwater runoff, which can have an effect on temperature and salinity. Runoff can also be a source of chemicals and pollutants,